right, so let's get started. Today I do want to do two more DP examples before we start the next topic, which is linear programming. One of these examples is a problem that you'll learn about NP completeness and NP hardness later in this class. It's an example of a problem that's NP hard. And it's an exponential time DP, but it's better than the most naive algorithm, which the most naive algorithm would be even worse than exponential time. And then the other one is of a flavor that's similar to, I'm giving something away, similar to something on one of your upcoming homework, so you might want to pay attention. Okay. So today, I'll finish DP. We won't spend that much time on it. Dynamic programming, and then two, we'll move on to linear programming. Okay, so one of the two problems I want to show you today for dynamic programming is what's called matrix chain multiplication. And here's the problem. So suppose we have a sequence of matrices that we'd like to multiply together. So for example, we might have a 3 by 3 matrix. And then here we have a 3 by 2 matrix, which means it has 3 rows and 2 columns, so it has fewer columns. It's more rectangular. 2 columns. And then we have, let's say, a 2 by 1 matrix, which looks like this. And these matrices are A, B, and C. In general, we could have a sequence of n matrices. And we know in this class that there are fast matrix multiplication algorithms like Strawson's algorithm. But let's say I just want to use vanilla for loops, right? So if I want to multiply an A by B matrix times a B by C matrix, the total time it would take with for loops is A times B times C, right? Because how many entries does the product have? The product is an A by C matrix, so it has AC entries. And computing each one of those is a dot product of length B. So the total time would be A, B, C. So now let's say we want the product of these three matrices. This is A times B times C. But this could be, if you remember from, I guess, is it junior high school when you learned like the law of associativity, right? You can choose how to parenthesize this. And no matter how you parenthesize it, you'll get the same answer. But your total runtime would be different. For example, if you chose to do A times B first and then multiply by C, how much time would that take? A times B is a 3 by 3 times a 3 by 2. That takes 3 times 3 times 2, which is 18 steps. And now you have a 3 by 2 matrix. And that 3 by 2 matrix times a 2 by 1 takes 6 steps. So this in total would take 18 plus 6, which is 24 steps, or runtime, if you did it this way. Whereas if you did A times B times C this way, B times C is 3 by 2, 2 by 1. That's 6 steps. And now you have a 3 by 1 matrix. 3 by 3 times 3 by 1 is 9 steps. So plus 9 is 15 steps. Right? So depending on the order you choose to carry out these multiplications, you can actually, speed up or worsen your total runtime. So what's the problem here? Okay. The problem here is, just let's keep track of dimensions, just so that everyone's on the same page. A is 3 by 3. B is 3 by 2. Right? So A times B is 3 by 2. And then C is 2 by 1. So this would be a 3 by 3 times 3 by 2 would be 18, and then a 3 by 2 versus 2 by 1 would be 6. So that's all I'm doing here. Okay. Now, so what's the algorithmic question? Given a sequence of matrices that I'm trying to multiply, I actually don't care what the matrices have written in them. I just want to know, given the dimensions of these matrices that I'm trying to multiply, what's the optimal way to do the parenthesization so that I minimize my total complexity to do all the multiplications? Okay? So that's the problem. So given, let's say, that we want to multiply A1 times A2 times AN, and AI is, let's say, SI by SI plus 1, what is the cost of the optimal parenthesization? Okay, that's the question. And we're going to do this with dynamic programming. And as I usually recommend, the approach I recommend is first come up with a function f, define it in words. What are you going to call f with to get your answer? Figure out a recurrence relation for f along with the base cases, and then analyze its complexity if you were to actually apply memoization or bottom-up DP. Okay, so right. Whenever you design these recursive approaches, I think it's always, I call it introducing order. It's useful to introduce order, right? So for edit distance, we said, look, you're trying to turn S into T. In particular, you first need to make sure that the first letter of S matches the first letter of T, right? So that's what I call order. Like there has to be a first, if you're going to optimize, then you have to make a first decision for the first letter. Here, what do I want to say? Well, if I'm going to do this parenthesization, there has to be a final multiplication that I choose to do, right? So for example, if I have a long sequence of matrices, A1 times A2 times A3, etc., if I choose, so there's going to be some order that I choose to do this parenthesization. There's going to be some final multiplication that's done. Let's say that the final multiplication that's done is this one. What does that mean? It means all of these things need to be multiplied first, and all of these things need to be multiplied first, right? So that means there's going to be some sub-parenthesization of this part, and also of this part. And then this lends itself to recursion, because now I'm asking, given that I've chosen to do this multiplication last, now what's the optimal way to combine these three matrices, and what's the optimal way to combine these three? And once I do that, I know what the cost of this will be, because the cost of this only depends on the first dimension of A1 and the last dimension of A3, which doesn't change depending on how I do this, etc. Okay, so you see here, if you recurse, here I say, suppose I choose to do this one last, within this part. Then I need to figure out how to optimally multiply this with this. Right? So we can see that all the recursive subproblems are basically going to look like subintervals of the matrices. Right? No matter how deep you recurse, you always have some subinterval of matrices left. So one will define Fij to be the optimal cost to multiply AI times AI plus 1 times times Aj, where here I is less than or equal to j. And we want, what do we want? We want f of 1n. We want to multiply everything. Okay? So that's what we're going to call our function with. Now what's the recurrence relation? f of ij equals, well, remember, we're looping over, by the way, we don't know which one is the last multiplication to do, right? We don't know what the best choice of last multiplication to do is. So naturally, what do? Brute force search. We try all possibilities for which multiplication would be the last one. Then we say, if this is our last multiplication, what would our cost be? And then we choose the min over all of those, right? Now, what would be the base case? When does this not make sense? It doesn't make sense if there's only one matrix, because then there's no multiplication to do. And the cost of combining one matrix is nothing. There's no cost. Right? So the base case is that I is equal to j. There's only one matrix. And the cost is 0. 0 if I is equal to j. That's our base case. Now, what's the recursive step? Well, how many matrices are in the range from I to j? J minus I plus 1 matrices, right? How many multiplies are in that range? J minus I, right? If you're saying multiply for me all the matrices between matrix 1 and 2, there's only one multiply between 1 and 2, right? So it's J minus I. So, and if we do, so let's just think about this. If we have I right here, and then here we have I plus 1, and then here we have j, we have all the multiplies in between. Here's a multiply in between. Here's a multiply in between. Here's a multiply in between. We're optimizing over the choice of which of these multiplies to do, right? Which means the smallest that our left interval could be after we do the multiply will be just containing I. And the biggest and the widest that our left interval could be is to go all the way up to j minus 1, right? So let's just optimize over basically the right. So there's going to be at the end two intervals, right? There's going to be let's say this is our multiply. There's going to be this interval, and there's going to be this interval. So let's just loop over what is the right endpoint. What is the right endpoint of the left interval? And we said that could be any number between I and j minus 1. So min over q, which is between I and j minus 1. So q is the location of this right interval, the last thing in the left interval, the last matrix in the left interval. Okay? So we're going to multiply I up to q, and then we're also going to multiply q plus 1 up to j. And then once we recursively do those, we have to combine them. Okay? So we have to combine I up to q. That's f of iq. We have to combine q plus 1 up to j. And then we need to multiply the resulting matrices. What are the dimensions of the resulting matrices? So again, the picture here, we have AI, AQ, times, and here we have AQ plus 1, AJ. So what are the resulting matrices dimensions? We said here that AI is SI by SI plus 1. So the left dimension, the row dimension of this matrix is SI. The column dimension of this matrix is SQ plus 1, which matches this. And this is SJ plus 1. So the cost to do that final multiplication is going to be plus SI times SQ plus 1 times SJ plus 1. So it's either 0, and this is otherwise. Okay, so that's the recursion. Base case, and then the recursive step. Questions? There aren't that many of us, so feel free to ask questions. So 3, runtime and memory. So runtime how many possibilities are there for I and j? Well, I mean, we only care so much about, let's in this class being right up to constant factors. So I can be anything between 1 and j can be anything between 1 and n. That's n squared steps. I mean, n squared possible inputs, right? N squared possible inputs there. Of course, that's an overestimate because I has to be at most j. It's the interval from I to j. So for example, if I is 7, j can't be 2. J has to be bigger, or at least as big. But it's still theta n squared possible inputs, right? Because basically the number of inputs is at least n choose 2, right? And that is already theta omega n squared. So theta n squared possible inputs. The time per input is certainly at most n, because we're looping over an interval of length j minus I, and j minus I is at most n. So you could say it's O of n time per input implies, in total, O of n cubed time. If you want to understand, is it actually theta n cubed? Maybe we were a little sloppy here with bounding j minus I by n. It really is theta n cubed. And maybe the easiest way to see that, again, you could do an exact summation. You could say, let me sum over all possibilities for I and all possibilities for j and sum of j minus I, and try to get an exact expression for that. But I do like to encourage you to be sloppy, right? So I'm saying if you want it to be exact time, you want to be more exact, is roughly the sum over all possibilities for I goes from 1 to n minus 1, or actually to n. The sum j goes from I to n of something that looks like j minus I. You could try to do this summation exactly and convince yourself that it's going to end up being n cubed. But if you're just trying to show that it's at least n cubed in terms of, in big O notation or in big omega notation, you can be even sloppier. You can say the following: look at look at the subset of possible inputs where I is between 1 and n over 4, or actually n over 3. I is between 1 and n over 3. There are n over 3 such possibilities, right? Now look at, for any such I, j is allowed to be between 2n over 3 and n, because all of those are bigger than n over 3. And for each one of those, j minus I is at least 2n over 3 minus n over 3, which is also n over 3, right? So I'm saying, I just want to say that this summation is certainly at least, it's certainly at most n cubed, and it's certainly at least the sum I goes from 1 to n over 3, the sum j goes from 2n over 3 to n of j minus I plus 1, because that's just the subset of the summands. And this, for this range, is always at least n over 3. So in total, this sum has n over 3 terms. This has n over 3. That's n over 3. So this is certainly at least n cubed over 3 cubes, which is 27. Okay, that's of course not the exact right computation. That's not the right constant factor. If you were careful about the sum, you'd get something more exact. But at least this shows that it's both O of n cubed and it's omega n cubed. So in total, it's actually theta n cubed. Okay. So this is an n cubed time algorithm. Yeah?
Where do we get to the j minus I plus 1?
Because basically, I just want to say that the total time you spend in this for loop is proportional to j minus I. But even in the case when I is equal to j, you still do spend constant time to just return the answer. So you're always spending time at least j minus I plus, or j minus I. Right? This for loop has roughly j minus I terms in it, or exactly j minus I terms in it. Right? Yeah. Or I mean, even if you drop it, it's still going to be n cubed. Any other questions? Okay. Anyway, I just did this sum this way just to show you that you don't always have to go for exact answers. It's fine to be sloppy sometimes when you're shooting for big O and big omega. So how about memory? Well, we already said that the number of inputs is n squared, so we need a table of size n squared. That's how many inputs there are. Right? And it's not clear to me how you would save on memory by doing bottom up. Right? Because, in some of the previous things like edit distance, we have this property that all the answers in one row depend only on the previous row, or all the answers in one column depend only on the previous column. But here we have, if we try to draw the DP table, let's say you have here I and j. So what does this answer depend on? It depends on all intervals that are contained within ij that either start at I or end in j. Right? So what does that look like? So let's say that these are smaller j's, and these are smaller i's. So this answer here, it depends on ij, but it also depends on ij minus 1, it depends on ij minus 2, etc. So it depends on this, and it depends on this. And then it also depends on the intervals that end in j with a smaller I. So it also depends on all these. Right? So you can't just keep track of one column or one row at a time. Right. But if you wanted to do bottom-up DP, it is always true that longer intervals are depending on shorter intervals. So you could process in bottom-up DP the intervals in increasing order of length, and you would always make sure to have the answers as you need them. Questions? So that's one example DP problem before I move on to the second one. Another problem, and by the way, so the source code, the Jupyter Notebook code that I was doing for live coding is all on the website. You can see the links, and it includes the code for both this problem as well as the one I'm about to do. And you don't need to install Jupyter Notebook to see it. Okay, so you can view it in the browser. So the other problem is the traveling salesman problem. So here, there are endpoints, x1 up to xj, and I want to start at point 1, then visit each other point exactly once in any order. Moving from xi to xj costs wij time, and I want to minimize total cost. And let's say all of these numbers are non-negative. Okay. So man, basically I have a complete graph, right? And I start at vertex 1, and I want to visit each other vertex in some arbitrary order. I'm allowed to choose the order, such that I visit each vertex exactly once. And I want to do that at minimal cost, right? So I'm a bus driver, or I'm an Uber driver, driving Uber Pool, right? And there are a bunch of people I want to pick up that are in different locations. and I want to get to them, but I want to minimize the total cost in doing that. So for example, if the people I want to pick up are these 6 people, it probably makes more sense to take a tour that looks like this, right, than to take a tour that kind of zigzags back and forth, because that's going to cost me more to zigzag back and forth, right? So the question is, in general, given endpoints, what's the optimal way to visit them all, starting at vertex 1? Does that make sense? So this problem is what's known as NP-hard. Okay, we'll learn about that more later in the class. But first of all, what I want to ask you is, right, the most straightforward brute force approach to solving this problem is, well, I don't know what order to try, what order is the best order to visit them all, so let me just try all orders. Okay? I know I'm starting at vertex 1, so the rest of the vertices I can visit in an arbitrary order. So how many ways are there to try visiting the other vertices? Yeah, n-1 factorial, right? And then for each one of those ways, I need to sum up the distances along that path, which takes me n time. So my total time is roughly n-1 factorial times n, which is n factorial. So the naive approach would be n factorial time. Naively, n factorial time. And we know from previous parts of this course that n factorial is roughly, root n up to constants root n times n over e to the n. Okay? This is like Stirling's approximation. There's a constant here that's like 2 pi or root 2 pi. Okay? But this is what it is asymptotically. Okay? And that's let me write this. I can write x as like e to the log x. So this is the same thing as e to the half log n times n to the n, which is e to the n log n, times e to the minus n, which is e to the n log n minus n plus half log n, right? Roughly. So this is an approximate, yeah. So this is definitely equal to that. So I mean, this is really the dominant term, right? This is worse than exponential. Exponential time would be like 2 to the n or 10 to the n. This is not 2 to the n. This is 2 to the n log n. So this is worse than an exponential running time. So if we can manage to improve the runtime to exponential, that would be a win. Even though normally we don't like exponential time, it's at least better than n factorial time. So we're going to do that using dynamic programming. So how are we going to do that? First, again, define the function f and ask ourselves what we're going to call it with. So define f of I comma s. Capital S is here. Capital S is going to be a subset of 1 up to n. Is equal to the min cost to visit all of s starting at I, or at xi. And what do we want? We want f of 1, we start at 1, comma, we need to visit everything else. So the set 2 up to n. So that's what we want. You can already see that there are a lot of states, because there's an exponential number of subsets. So let's write a recurrence relation. So here, we can say that, look, f of is, what's the base case? The base case is when there's nothing left to visit. So S is the empty set. If there's nothing left to visit, it costs us 0. Okay? Otherwise, we basically just loop over who's all choices, brute force search. We know we're at I. We know we need to visit everyone in S. Who's the next person that we're going to visit? I don't know, so let's try them all and pick the best one. So this is the min over all j in S of the weight going from I to j, plus now we're at j, and we're trying to visit everything else. And that's it. Simple enough. That's also implemented in the code. You can see on the website if you want. One nice thing of, if you want to implement like subset stuff in code, one hacky way to, well, not hacky, but I guess one way that minimizes the amount of code you have to write is to represent sets as ints, right? So if I have a number that looks like this in binary, so any int can be written in binary, right? And then I can write 1, let's say 0, 0, 0, 1, 1, 0, 1, 0, 1, 0. I can interpret this as a set, right? So if this is element 1, and this is element 2, and this is element 3, and this is element 4, etc., what this means is it's the set containing 2, 3, 5, 6, and 10, right? And then if I want to check whether or not something is in the set, I can do some bit shift and then bitwise AND to see whether or not that bit is set to 1. If I want to add something to the set, I can just OR it in, right? So for example, if I say, look, take S or 1 shift I, what this means is take that int and then OR in a 1 at the ith position. So that's basically adding I to the set. Anyway, you can take a look at the code if you want. This is more of just an implementation trick. But anyway, this is the recurrence. And then now, let's ask ourselves about the runtime and the memory. So the runtime, first, let's do the memory. How many inputs are there? N possibilities for I, and 2 to the n possibilities for S, because there are 2 to the n subsets. In fact, actually, even 2 to the n minus 1, because we know 1's never going to be in there. But basically, it's roughly n times 2 to the n. So n times 2 to the n. And then the runtime, for each of these possible inputs, I need to loop over all j, which could be, it's a loop over at most n things. So this is something like n squared times 2 to the n. Okay. If I wanted to do bottom up, notice that subsets only depend, the answer to a given subset and j only depends on subsets which are 1 smaller in size. So I could process bottom up, I could process all of the inputs in increasing order of size of S. Okay. And I can first fill in all the ones that were sets of size 1, then all the ones that were sets of size 2, or all the ones sets of size 3, etc. And if you do that, basically, you only need to keep, again, kind of one row at a time, but this row contains all sets of a given size. So what's the maximum? So if I ask you, look at all the sets from 1 to n. Look at all the numbers from 1 to n. How many subsets are there? There's 2 to the n, right? How many subsets are there of size 1? There's n choose 1. How many are there of size 2? N choose 2. Size 3, n choose 3. So my space is going to be proportional to the largest possible value of n choose k, right? Okay. And that happens when k is n over 2. And n choose n over 2, so bottom up can get space about n times n choose n over 2. And n choose n over 2, it turns out, this also follows from Stirling approximation, is roughly 2 to the n over root n. So this is roughly root n times 2 to the n, which is a little bit better than n times 2 to the n, but it's still exponential memory. Okay, so that's all I wanted to say about DP before I move into linear programming. Any questions? Yeah. Well, some rows are cheaper, right? The kth row only costs unchoose k, but I mean, in the worst, yes, but there's a point in our algorithm where we need to actually remember a row of size n times n choose 2, n times n choose n over 2. So that dominates our total space, just remembering that middle row. Okay. So I want to switch to linear programming. So linear programming we're going to be looking at problems of the following form. Let's say C is a vector, B and C are vectors, A is a matrix. Minimize, and I'll make this less abstract very soon. Minimize C transpose X, subject to the constraint that AX is at most B. Okay, and also, yeah, let's do that. Right. So C transpose X, right? C transpose X just means C1 x1 plus plus, let's say, Cn xn. And when I say Ax is less than or equal to B, if X is a vector, Ax is a vector. A is a matrix and X is a vector, so Ax is a vector and B is a vector. What does it mean for a vector to be less than or equal to another vector? I mean every entry. The first entry of this vector is less than the first entry of this one. The second entry is less than the second entry of this one, etc. And let me make this concrete. Okay. So here's a concrete fake example. I own a store that's going out of business. Okay? I own a manufacturing plant that's going out of business, but I still have some supplies or ingredients left to manufacture stuff. I want to at least use that to manufacture stuff and sell as much as I can before I close shop. Okay? So my factory makes two products. Product one is something called foo. Okay? It sells for $4 per ounce. Okay? And in order to make 1 ounce of foo, it costs me, or it takes 1 ounce of butter, 2 ounces of water, and 4 ounces of goo. Okay? And then my other thing that my factory makes is bar. And this sells for $5 per ounce. And making 1 ounce of bar costs it takes 6 ounces of butter and 3 ounces of goo. And given that I have a certain leftover amount of water, butter, and goo stockpiled, what's the maximum amount of money I can make by manufacturing foos and bars? So what remains is W equals 10 ounces of water. And let's say B equals 6 ounces of butter. And G is equal to 6 ounces of goo. So what's the max profit I can make? Well, I can write down a linear program. Okay. And actually, let me even enforce, I'm also going to say that, let's say all the entries of x have to be non-negative. What does the linear program look like? Well, I want to maximize my profit. Right? For every ounce of foo I make, I get $4. And for every ounce of bar I make, I get $5. So I want to maximize 4x plus 5y. So here I have two variables, right? I basically have x1 and x2, or x and y. So I have c1 and c2. c1 is 4, and c2 is 5. But subject to certain constraints. So what are the constraints? Well, of course, if I'm trying to maximize my money, I'll just make infinite foo and infinite bar. Well, I can't because I only have 10 ounces of water, et cetera, et cetera. So I can't make more than what I can afford to make given what I have remaining in my storage. Okay? So for every ounce of foo I use, for every ounce of foo I manufacture, I use up 2 ounces of water. So if I make x ounces of foo, I use up 2x ounces of water. And I don't use up any, for every bar I make, I don't use up any water. Bars don't take water. So 2x plus 0y has to be at most the amount of water I have. I only have 10 ounces of water. So that's one constraint. So there's a constraint for water, there's a constraint for butter, and there's a constraint for goo. So what's the constraint for butter? 1 times x, because making 1 ounce of foo costs 1 butter. 1x plus 6y is at most 6. And then finally I have 4x, because every ounce of foo I make uses up 4 goos, plus 3y is at most 6. And I also have the constraint that x and y have to be at least 0. I'm not allowed to make negative stuff. There's no such thing as making negative items. Okay? And now what is this really saying? Let's try and draw a picture. So this is the picture here. This is the amount of ounces I'm making of foo and the amount of ounces I'm making of bar. So we know that x has to be at least 0 and y has to be at least 0. So actually, let me get another color. So x has to be at least 0. What does that mean? It means that, so at the end of the day, we're going to choose to make some amount of foo and some amount of bar. So we're choosing a point at the end of the day, right? So what are the constraints for this point? We need to make sure x is at least 0, which means you have to be on this side of this line. And also that's that y is greater than or equal to 0. So y is greater than or equal to 0 means you have to be in this half space. And similarly, x has to be greater than 0, which means you have to be on this side of the line. You also have the constraint that 2x is at most 10. In other words, x is at most 5. So let me label this grid. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. So x has to be at most 5, which means x has to be at most 5. So what is that? That's this line. You have to be on this side of it, right? And then you also have that x plus 6y is at most 6. So that's some line. What's that line? Let's think about where the x and y intercepts are. When x is 0, y is 1. And when y is 0, x is 6. Actually, I could do that, but let me slightly change it to make the picture a little prettier. No, I'll do that. I'll leave it like that. So here's 6 right here. So that's basically saying this line. Right? You have to be on this side of this line. And then there's also 4x plus 3y is at most 6. What are the x and y intercepts of that? When x is 0, y is 2. When y is 0, x is 3 halves. 6 divided by 4 is 3 halves, which is right here. So that's this line. And you're saying you have to be on this side of that line. So at the end of the day, the constraints say that you have to be in this region. The point you pick has to be in this region, which is some quadrilateral. In general, it's always going to be a polygon, right? The intersection of a bunch of half spaces, if it's bounded, is going to be a polygon, or it might be a polygon that's unbounded in certain directions. And you're trying to maximize 4x plus 5y. 4x plus 5y is this direction. 4 plus 5 is right here. It's this direction. And what do I want to say about this picture? Well, kind of what that is really saying, if you want to give like a physicsy kind of interpretation, is imagine you take this picture and you rotate it so that this is pointing down. This is like gravity, so gravity points down. So rotate this picture so this points down, and ask yourself, if I were to drop a marble inside of this polygon in this region, where would the marble wind up, right? It would fall, maybe hit a side and start rolling, but eventually it would get stuck in a corner, right? Where would it get stuck? That's the question. And in this particular example, it would get stuck right here. So right here is the optimal solution. Okay. Yeah? Wait, no, maximizing the total volume of what's made. So maximizing the total volume of what's made would be like max of x plus y, which is not, maybe that would give you the same thing in this example, but in general, no. Like if I change the numbers slightly here, I could probably rig up something where max x plus y and max 4x plus 5y wouldn't give you the same thing.
Oh, okay.
Yeah. And you had a question. It might not be. You said, what if the optimal point doesn't have integer coordinates? It might not. Yeah. How do you know that a vertex is the optimal point? I think proving that is beyond the scope of this course, but we're just going to take it for granted. But, I mean, from a physics perspective, it makes sense, right? So there's always going to be, for example, like if I drop, so let's imagine that there's like some shape, right? And I drop a marble in that shape. It's going to roll to the point of lowest energy, which is like a corner or a vertex. It might be the case that like here, if I drop it here, this is actually completely flat, right? But even here, there is a vertex which is optimal, which is like this one. Right? Imagine that there was actually a shield that rose up here. There always will be a vertex which is optimal. If you're not, if you're unlucky and like one of the sides of the polygon is completely flat on the ground, then when the marble hits, gravity is not going to make it roll further. But if your polytope is what's called in general position, let me not formally define it. However, let's imagine that you take whatever problem you have and you just randomly rotate it just a little bit, randomly rotated by epsilon. Then with probability 0 will you have any flat surfaces. So you'll always roll to the bottom of some corner. That's very physicsy and not a proof, but I think that's as that's as rigorous as I'm going to be for this question. Yeah.
Does that analogy change if you're not playing like the max or the min? In this case, we're playing the max, but like, say like sometimes you want to find the min.
Right. So you're saying, does it change if I want to find the max versus the min? But notice, I can always convert max to min and vice versa, because if I'm saying max C transpose X, that's the same thing as min D transpose X, where I just set D to be minus C. Just like negate each entry of C. That will turn max into min and vice versa, right? So I can always, without loss of generality, assume that it's max. Any other questions? Okay. So algorithms for this problem. Also, I guess one thing I also want to mention is, maybe it's also useful to know, so I'm not going to prove it, but I mean, the intersection of a bunch of half spaces, as I mentioned, is always like, it's a polygon in 2 dimensions, and higher dimensions is a polytope. Okay? It's always what's called convex. So the feasible region, so this here is what's known as the feasible region. It's the set of xy pairs, or it's the set of points that satisfy all the constraints, right? All this pink region here is what's called the feasible region, right? And the claim is that the feasible region, which I'm not going to prove, is always convex. What does convex mean? Convex means if you take 2 points in the region, the line connecting them stays in the region. So for example, you could ask, could this ever happen? Could the feasible region ever look like this? Like this region in here? Right? That can't happen. And in fact, if you dropped a marble here, it's not necessarily going to fall, gravity, let's say gravity points down, the optimal place would be right here. This would be opt. But if you drop the marble right here, it might get stuck here. Okay? So luckily that getting stuck can't happen if you're in a convex place. Okay? So feasible region will always be convex. Right? And why is meaning the line between any 2 points stays feasible, stays in the feasible region. That's not true here, right? If you take this point and you take this point, the line between them, it exits the region, right? Which is bad. That's not convex. So algorithms for this problem. Algorithms. So the first algorithm that was developed is called the simplex algorithm. That was by Danzig in, I believe, the 40s. And it's a greedy algorithm. Okay. So what does the algorithm say? His algorithm says, so I have some polytope. So let's say in 2 dimensions a polygon. I just start at some vertex, and I just keep greedily walking to an adjacent vertex as long as it improves the objective function, as long as it improves 4x plus y, 5y. So I say, which of my neighbors here improves 4x plus 5y? And I just keep moving in that direction until no neighbor improves it. Okay, and then I just declare this is the optimal thing. Now, it should be confusing how this works because how do you get the starting vertex? That's not obvious how to get a starting vertex to begin with, right? In particular, think about this. Min 0 transpose x, subject to ax is at most b, and subject to c transpose x. Negative c transpose x is also like or let's say C transpose X is at least Q, and X is at least 0. Right? If I could find a vertex of this, I mean, notice that the objective has nothing, or like I said max, not min, max. Right? This is just a linear program, but if this were my original linear program, I could say, what is the optimal value I can achieve? I don't know. Let me find it via binary search. Right? And then if I want to say, well, can I achieve Q? I can just write this down. Max 0, subject to AX is at most B, and C transpose X is at least Q. If I could find a valid solution for this, it would tell me that, yes, you can achieve Q, and then I can do my binary search. So it shouldn't be that easy to find a vertex, because if you could find a vertex, you could solve this problem, which means you could solve that problem just by binary searching on Q. Right? So finding even one feasible point is like basically essentially just as hard as optimizing the whole thing. So what's Danzig's trick? The idea is as follows. Look, first of all, if I have something that says max C transpose X subject to AX is at most B and X is at least 0, I can define, in my mind, I can think, look, let me define some SI to be BI minus AXI. Right? The ith entry of this right-hand side is BI, and the ith entry of the left-hand side is the ith entry of AXI. What do I know? I know that this has to be less than or equal to that, which means this has to be greater than or equal to 0. So I call this SI, so I can just write, look, this plus S is equal to B. And again, S has to be at least 0. Every entry of S has to be at least 0. Right? So I can convert this original LP into like this format. And this itself, I can basically make a new vector. So before I had X, and I had A, actually let me write it like this. Before I had A, and I had X, and now what I have is A together with an extra column that's 1, 1, 1, 1. And here what I have is, or actually it's more like the identity matrix. Actually, let me give myself more space. So before I had a matrix A here times some vector X is at most B. And then I can transform that into the following thing. A, but here I'll tack on the identity matrix 1, 1, 1, 1, 0 times X. And here I'll just tack on S is at most B. Does this make sense? What does this mean? So the first dot product is going to be the first row of A dotted with X as usual plus S1, right? So AX1 plus S1 is equal to B1. And similarly, AX2 plus S2 is equal to B2. Is equal now. And let me just give these new things names. This I'll just call A tilde, and this I'll call X tilde. So what I have at the end of the day is max, and then I can also make a new C. C tilde is just the original C with a bunch of zeros tacked on. So I can say max C tilde transpose X tilde subject to A tilde X tilde is equal to B, and X tilde is at least 0. right? So what this says is, sorry, I wrote min here, but I was actually maximizing over there, wasn't I? It's all the same because I could always negate C. Min and max are the same up to negating C. So the point is, optimizing an LP that looks like this with inequality constraints is equivalent to optimizing a similar size LP with equality constraints. Okay? So that's the first step of simplex. And then now you need to have a starting vertex. So I'll modify it. So let me write down the following LP. Minimize t is just the number, subject to a tilde x tilde is equal to 1 minus t times b. And 0 is less than or equal to t is less than or equal to 1, and x tilde is at least 0. What does it mean to minimize t? Well, ideally you want t to be 0, because t is constrained to be at least 0. So if you minimize t, what you're saying is a tilde x tilde is equal to b. Does it make sense? Good. So that's it. So now we can say, look, if I want to, and if once I find an x tilde that said a tilde x tilde is equal to b, I have an x tilde that actually is feasible, and then I can use that as my starting vertex for simplex here, and then run simplex greedily. But I need to have a starting vertex here. So here, what's my starting vertex going to be? X tilde is equal to 0, and t is equal to 1. Okay? That's definitely a valid solution, because I have a tilde times 0 is equal to 1 minus 1 times b, so that's 0 is equal to 0, and it satisfies all the constraints. So basically, in order to get a starting vertex for the original linear program to then do simplex, write this new modified linear program, start with this vertex, now run simplex on this linear program to minimize t. It's going to give you an x tilde that actually is feasible. Take that x tilde, bring it here as a starting vertex, and run simplex here greedily. So you're basically going to do two simplexes. Okay. So I know I said a lot of simplexes and stuff. Questions? Yeah. That means t equals 0 is not achievable, which means that the original LP was not feasible. So you should basically output no solution. There is no solution to the original LP. That's a good question, because this is an example where the feasible region was non-empty. But imagine that you had an LP that said one constraint was x is at least 5. The other constraint is that x is less than or equal to 3. You can't be less than 3 and bigger than 5 at the same time. So the correct answer is there's no solution, right? So that can happen with linear programming, where there's no way to satisfy the constraints. And then you should output no solution. It can also happen that there's an unbounded solution. So suppose my LP looks like maximize x subject to x is at least 0. What's the answer? It's infinity. I can make x arbitrarily big. So that's what's called an unbounded linear program. So it could be unbounded, it could be infeasible, or it could be bounded and feasible and then have an optimal solution, which is something finite. Yeah? Oh, that's zero. All zeros vector or transpose. So basically, what I mean by zero Oh yeah, so all I was saying here was this. That means basically 0 times x1 plus 0 times x2 plus da 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 plus 0 times xn. Okay? Oh yeah, all I was saying was optimizing an LP is just as hard as just figuring out some feasible solution to the LP and vice versa. They're just as hard as each other up to this having to binary search, right? Because if I can solve the feasibility problem, I can then throw a binary search on Q on top of that to get the optimal solution to this problem. Does that make sense? Yeah. Why 0? Because by putting 0 there, it basically means I don't care about the objective function. Right? So again, so what I'm saying there is finding some solution. So at the end of the day, there's some big polytope, right? There's this big space, and somewhere living in that space is some polytope. Right? Now, if all you give me for the problem input is you tell me the matrix, you tell me A, you tell me B, and you tell me C, and you're saying now, find the optimal thing in this direction, there are really like two things I have to do here, right? One is, first of all, just like find any point in this polytope at all, right? And then find the one in the polytope that's optimal, right? There's like two possible problems here, right, that I could consider. One is find anything in this polytope at all versus find a thing in the polytope which is the max in this direction. Now, it seems like the second problem should be harder, right? Find any point at all versus find the best point. I mean, finding the best point is a specific kind of point. That should be harder than finding any point. But what I'm saying over there is actually it's not really harder. Finding any point at all is pretty much just as hard as finding the best point. Because I can encode the quality of the point as a constraint, and I can set the objective to just be 0. I can just not care about the objective. And then if I'm able to find a point in this polygon, or in this polytope, it means I found something whose value is at least Q. Right? And then I can binary search on Q. I can basically repeatedly solve LPs each time I adjust the LP by changing Q via binary search. And then ultimately I can find the optimal Q this way. Right? So I just wanted to say that those two problems are equivalent. Finding a point versus finding the optimal point are essentially equivalent up to binary searching. Okay, so I said enough maybe about that and simplex. One thing I do want to say about simplex is like what's some kind of bound I can give on the runtime? Well, I always start at a vertex, and I move to a better and better and better vertex. One bound I could give on simplex is, well, the runtime is certainly at most the number of vertices in the polytope. Unfortunately, the best bounds we have on that are exponential. Right? So, and in general, we actually don't, as far as we know, simplex is an exponential time algorithm. There's no, and there are some choices to make, like, okay, I'll greedily move to the better vertex. That's a neighbor of me, but there might be many vertices next to me that are better than me. And people have explored different, how do I make that choice? Do I move to this better vertex or do I move to that better one? And there are different kind of what they call pivot rules, basically rules to choose which vertex I move if there are multiple next to me that are better. Okay, and even to this day, we don't know any pivot rule, any greedy strategy that gives you a runtime that's better than exponential. All our implementations of simplex are exponential time. However, people do still use simplex in practice because on real-life inputs, it often does run fast, even though in the worst case it could be exponential. Okay, so that's simplex. There's another algorithm, or two more. One is the ellipsoid algorithm due to Kachian in the 70s. And this was the first polytime algorithm for linear programming, right? Roughly 30 years after the simplex algorithm. And even though this is polytime, whereas simplex is exponential time and everyone uses it, ellipsoid is polynomial time and almost no one uses it, right? Because it's one of those things where, yes, simplex is exponential in the worst case, but it's usually fast. But ellipsoid is such that it's basically always slow, okay? I mean, yes, it's polynomial, but like n to the sixth, is that a great polynomial? Okay, probably not. Right? I mean, we know other algorithms like that from class where it's basically, we prove a certain bound, but it could potentially run faster. Like, for example, or like we prove a bound and it always runs in that time. For example, merge sort. Merge sort will always run in n log n time. It doesn't matter. Even if your input is already sorted, it'll run in n log n time. So that's something that always runs in the time you say. That's kind of like ellipsoid. It's basically always slow. Okay? Whereas if you take something like insertion sort or bubble sort, that could be n squared in the worst case. But if your input's already sorted, it's actually linear time. So there are nice cases where it's actually fast. And that's kind of like what's happening with simplex is like, yes, it could be exponential in like bad cases, but those bad cases usually don't happen in real life. It's usually fast on the kinds of inputs you actually see. And then after that was the interior point method, which is due to Karmarkar. And this stuff, I'm just saying it for your own knowledge. I think this was in 84. This is a polynomial time algorithm that people actually do use. And it solves things even more general than linear programming, other more complicated types of optimization problems. Same thing with ellipsoid. Polytime and more practical. Okay. In the last 6 minutes or so, I want to introduce one more concept that's important related to LPs, and then we'll go into we'll see each other again on Tuesday. So the important LP concept is something called duality. What is duality? So the idea behind duality is I want an automated way. Again, let's go back to that example where I'm trying to make foos and bars, and I'm trying to maximize my sales, my money. So at the end of the day, what I really want to know is like, what's the maximum amount of money I can make? And the answer to that is this. But to get that answer, maybe I need to actually have a code, an algorithm that solves linear programs. So is there some simpler way to prove to me a bound on what I can make? Like, is there a way to prove to me that Jelani, okay, I don't know what the optimal thing you can do is, but I can certainly prove to you that there's no way you can make more than $100, right? So is there an automated way to generate these kinds of statements? These kinds of upper bounds. There's no way you can make more than blah. So here's a way to do that, to kind of in a sort of automated way or systematic way, prove to you that it's impossible. So we said 2x plus 0y is 10. 1x plus 6y is 6. And 4x plus 3y is 6. And xy is at least 0. So, look, suppose I multiplied, this is all less than or equal to. Suppose I just multiplied each equation by, and actually let me just, for the simplicity of this example, let me get rid of these. Suppose I multiplied each inequality by a non-negative number on both sides. So I multiplied this by z1 and I multiplied this by z1. And I did the same thing here. I multiplied both sides here by some z2, and this by z2, and these sides both by z3 by z3. And then I added it up. And when I added it up, what do I get? I get that first, so because all of these z's are non-negative, it doesn't flip the direction of the inequality, right? If I multiply both sides of an inequality by a negative number, the direction flips. But if I insist that all the z's are non-negative, the direction won't flip. And then let me just add this up. So if I add it up, what I get is 2x, let's say z1, 2x plus, da, 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 da. So 2z1 plus z2 plus 4z3 x plus 6z2 plus 3z3 y is at most 10z1 plus 6z2 plus 6z3. Right? That's what I would get. Now, I'm allowed to choose z1, z2, z3. Right? So what I want to do is, I want to choose them so that this is equal to 4. And this is equal to 5. What does that imply? It implies that 4x plus 5y, which is my objective, is at most some number. Right? So I've just proven to you, for this particular choice of z1, z2, z3, I've proven to you that it's impossible to make more than this number of dollars. Right? So that inspires what's called the dual linear program. First of all, what are the coefficients on the right-hand side? They're the coefficients over here, which is b. That's the vector b. Right? And I'm trying to convince you of the best upper bound possible. I want to make that number as small as possible to convince you that, that you can't make that much money. So I want to minimize b transpose z, subject to the constraint that it turns out with this, so basically you want this dot product to equal, what is this? This is C1, right? 4 and 5, that's the vector C. C1 is 4, C2 is 5. You're saying you want this dot product to equal C1, and you want this dot product to equal C2. What you're really saying is you want A transpose Z to equal C, and you have the constraint that Z is at least 0, because otherwise you would flip the signs of the inequalities. This is the dual linear program. This is what's called the dual. And the reason duality is so important is because of two things called weak and strong duality. So let's label things. There's what's so-called primal LP, which is that you want to max C transpose X subject to AX is at most B. And you have what's called the dual LP, which is you want to minimize B transpose Z subject to A transpose Z is equal to C and Z is at least 0. This is the dual. Weak duality theorem, weak duality is that opt of the primal is at most opt of the dual. That's kind of by definition, right? We constructed the dual in such a way to ensure that any solution to the dual costs at least as much as any solution to the primal, because the dual was constructed to give upper bounds on the amount of money we can make. So it's not just true for the opt, it's true for any solution. Any solution to the primal is upper bounded by any solution to the dual. And there's something that's even more powerful. That's kind of a triviality. That's by definition. There's something more powerful called strong duality. Which says if the primal is bounded and feasible, so its feasible region is non-empty and it's a bounded polygon, it doesn't go off to infinity, polytope, then actually the opt of the primal is equal to the opt of the dual. Whichever one you optimize, you'll get the same thing. The proof of that is highly non-trivial and is definitely beyond the scope of this course, but it is something that I want you to be aware of. And there are going to be, even though you're not responsible for understanding why that's true, that fact that the opt of the primal equals the opt of the dual, we may give you questions at times where you're expected to invoke that fact. Okay, so you should make sure that you know that fact. Okay? Any questions? Yeah.
Does it matter where we choose our starting vertex to be in simplex for a bounded region, or is that just an optimization to have one that's closer to?
Right. So the question was, does it matter where you start your starting vertex in simplex? I mean, the closer you start to opt, the better, but you don't really have control. You don't know that, right? So
That whole 1 minus t, what was the purpose of that?
that was just to give you, because when you optimize that, you're going to end up with t equals 0, which is some vertex for the original. So it's a vertex of this new fake LP that I created. That's going to be some vertex for the original LP. It tells me nothing about its cost, because that LP I set up with t didn't even talk about the cost. So that thing might not have good cost, but at least I know it's a vertex of the original LP, and then I can start from there.